Now we meet what is perhaps the most important probability density function in all of mathematical statistics, the normal probability density function. Credit for this distribution goes to Carl Friedrich Gauss for his work in 1809, and is sometimes called the Gaussian distribution. If you take physics, you will find Gauss made many fundamental contributions there and also in pure mathematics. We begin first by discussing discrete random variables. The Poisson is sort of a hybrid case of a discrete random variable and a continuous random variable, however. We then met the continuous distributions, the uniform, admittedly a bit of a letdown, and then the exponential. This distribution did provide probabilities that have great usefulness for a whole class of processes. We are able to find probability of any process that has a service time. We can find probabilities of time to failure for parts, or waiting time in line, or for your restaurant table, or for a telephone call, or internet connection. The normal probability density function is for continuous random variables, and the normal distribution has an important distinction from the previous probability functions. They are all defined for specific processes, specific experiments. The binomial is a good example of this. We can calculate probabilities for any binomial process with this distribution, but it will be no help if the process is not binary, meaning there are only two outcomes, success and failure. All our previous distributions also have the same requirement. They work if, and only if, the experiment matches the assumptions of the distribution. The normal distribution is not based on a process, but simply tells us the probability of a particular event if the random variable is normally distributed. If the random variable is not distributed in accordance with the normal probability density function, then we cannot use this probability density function to compute probabilities, except approximately, and then only in specific cases. The default for a dataset is not the normal distribution, as I'm afraid we have seen in too many approaches. Remember, the difference between statistics and probability is that in probability we know all that there is to know about the random variable, including whether or not it is normally distributed. By the end of this unit, you will be able to identify cases where the normal distribution is relevant and where not. You will be able to calculate probabilities for normally distributed random variables, and you will be able to use the normal distribution to estimate probabilities that are binomially distributed. You will be able to read and use the standard normal table to calculate these probabilities, and understand the relationship between the number of standard deviations on a standard normal table and the number of standard deviations in an actual normally distributed population data.